Morning, everyone. My name is Panagiotis Sarandi, and I'm here on behalf of the University of Patras, the lead partner in the Germ of Life project. And we are here, and I'm welcoming you in the first Germ of Life webinar. So thank you all for joining us today and for the first technical webinar of the Germ of Life project. That is titled Drought Analytics in Practice, Indices, Forecasting and Regional Implementation. So, as I said before, I'm Panagiotis Sarandi, and I will be coordinating today's session. So, as many of you know, this is an important milestone for our consortium, since we are in the German project and we are trying to work on drought resilience. And today we explore the scientific foundation of our project and how we plan to move forward. So let me start with the first presentation. It's actually mine, so give me a few minutes. We will proceed with the opening of this seminar. So, start with plainly an introduction of our project and what we are planning to discuss today. So, as I mentioned on today's presentation, we will be dealing with drought analytics in practice, indices, and forecasting regional implementation. What we are mainly wanted to discuss is why we are here. So, as you know, drought is intensifying across the Mediterranean region. So there are increasing impacts on agriculture, water resources, and ecosystems. So there is a great need for a shared understanding of monitoring, prediction, and risk tools. So with this webinar today, we built the scientific foundation and the technical foundation for collaboration. We are trying to showcasing you our examples and how we are moving forward within the project. Main words on what is our challenge, what is our Mediterranean challenge. As you know, it is more frequent today, the drought events that are occurring every 1 or 2 years. So there are longer dry season and rising temperatures. This is leading us to unpredictable climate patterns. So this complicates planning. So what we are aiming to do is give some kind of tools to regional authorities for them to always implement, maybe in the future, include them in their plans. So there are also one of the main challenges that there is socioeconomic risk for communities, farmers, and natural landscapes. And this has led us to the issue that we are studying. So what is Germany? If you know it since you are here with us today, Germ of Life is an inter-Euromed project that is developing a preventive drought risk management approach. As a project, we aim to integrate climate data, ground sensor, and satellite indicators and AI. So this turns environmental signals into actionable regional insight, that is our main goals, and helps a region shift from crisis response to strategic resilience. So what is our vision? What we're aiming to do is transform data into practice knowledge from decision makers and enable early detection of drought signals. this will lead to the support of long-term climate adaptation strategies. And of course, we are aiming to strengthen cross-border cooperation and share Mediterranean resilience. So what we deliver as a project, that is our main issue, and some of them will be discussed later today. So we have the drought prediction tool that is based on SPEI and DVI and real-time and forecast data. We have the vulnerability assessment tool that is mainly an ecosystem and sector risk scoring, And we have the innovation procurement platform that connects regions with natural-based solutions and tech solutions. And of course, this is all based around specific pilot sites. So we are also doing real-world testing in Greece, Italy, Portugal. We have specific 4 pilot sites, one in Greece and Italy, that is a traditional 1 year exposed prolonged summer drought. We have one in La Valle Park in Italy. It's a meadow ecosystem sensitive to drought and extreme conditions. And we have one in Alvito, Portugal. It's a Mediterranean temperate pond, so highly climate dependable. And we have the final one in Andalusia in Spain that is currently under construction. So this contrasting site ensure model robustness and regional relevance. But why start with indices? So as you know, we're starting today's seminar with some basic information because indices reveal early drought formation across climate, soil, and vegetation. It standardized indicators make regions comparable. That is one of our main issues that we want to discuss within the project. We support monitoring, reporting, and early warning system, and they are essential for building the predictive models and risk forecasts. So why also forecasting matters? It is one of our main key points in this session and also within the project. Forecasting gives advanced warning of high-risk periods. It also supports agricultural scheduling, irrigation planning, and resource allocation. It helps authorities activate mitigation measures, and it can lead to reduced economic losses and environmental pressure. So this is pretty much about the project itself, but let's have a first look on what we are focusing on today. So today in this webinar, we are focusing on understanding drought indices and how they are calculated. We are exploring the forecasting tools and predictive modeling. We are learning from early insights in the pilot sites we have in Greece and Italy. And we are linking scientific analytics with regional implementation based on a speech we have from a keynote speaker that is focusing on the vineyards sector. That is our main goal in the Greece pilot, our main action actually. Today's agenda, more or less, it's we have, as you know, the welcome we're doing right now. We have the first presentation about drought indices and monitoring. We are then moving forward into forecasting models. Then we have the pilot showcase with Greece and Italy. And of course, we have a keynote speech on drought and viticulture. And of course, at the end, we have a short Q&A for us to discuss from insights from you that you're here today taking part in this webinar. So about our speakers, I will say a few words, mainly introduce them, but as we move forward, I will introduce myself. We have first Ms. Manuela Balzarolo from CMCC. She will talk about drought indices and remote census. We have Ms. Leah Duran from Ethos, from France. She will discuss forecasting and modeling. Of course, we have from our University of Patras, Professor Giriou, discussing the Greek pilot, and from Lamoro, the environmental agency, we have Ms. Sonia Ableton that will discuss the Italian pilot. And of course, closing, we have Professor Stefan Skouras from the University, Aristotle University of Thessaloniki, that will have a keynote speech on the wide sector and how drought affects it. So, what we are aiming to have in this webinar, the value that we are aiming to have is to create a shared technical language across the partners, establish an analytic basis for future tools, help the regions understand how the data improves preparedness, and strengthen collaboration for long-term resilience. So what we're discussing is a scientific foundation, practical tools for authorities, tools refined through pilot testing and stakeholder engagement. We will do the future webinars that we're planning, and of course, we're aiming to have continuous knowledge exchange across the Mediterranean partners. So let's begin our seminar. Thank you so much for being here once again. We have our first presentation now. Let me stop sharing my screen. From Ms. Manuela Bazzarolo.
Yes.
So thank you for being here. Ms. Manuela is working with CMCC in Italy, and she will be discussing the drought indices as a measure forward. So Manuela, you are free to share your screen.
Yes, thank you, Panagiotta. So can you see my presentation in full mode? Yeah. Okay, so can you hear me well? Okay. So I will start with this presentation on the computation of different draw indicator using different techniques. And thank you very much to Panagiotta for already introduced some of the basic concept that I will also use in this presentation. And I'm a senior scientist at the Foundation Euro-Mediterranean on Climate Change in Italy, and we are working on the effect of climate change on different sectors, and in particular on ecosystems. And in the Germ of Life project, we support the scientific development of the indicators, and we share knowledge on the impact of droughts on ecosystem. As already was shown by Panagiotta. So in the last decades, we have a very increase on the frequency in droughts, mainly in Mediterranean area. And we know that Mediterranean area is an hotspot of the climate change. And the one of the big issue is also that we have an increase on the intensity. So we have a more and more huge impact and severe impact on ecosystems. And this affect clearly the production of for food for our agriculture from our agriculture sector, and of course sorry, I don't know why it started in this way. Sorry, I don't know why it goes in this way, but so I need to. Okay, but anyway, so just coming back, sorry, and for the water resources, so there is a big competition nowadays in everywhere in the world, and mainly in the Mediterranean area, because we have this huge demand in water for the increase of demand for agriculture, mainly, and also for people, because people needs to also have a drinkable water during summer period as well. And this provoke, of course, very huge consequences in economic and in the Mediterranean area, mainly where we already face with strong and current economic crisis. So what we did first in the Germ of Life project, it was to characterize the droughts. So from scientific point of view, we have different type of droughts. So we can talk about meteorological drought, hydrological droughts, and agricultural droughts. This is the first natural step that we had to do at the beginning of the project to first try to focus on the common aim and also to, sorry, I don't know why I have this animation that start. Sorry, I don't know what's happening in the presentation, but yeah. Maybe I do in this way just to stop a bit the presentation and focus more on this part, because as we have this different type of droughts, and what is very important, it's to talk and understand well each other, because when we spoke about meteorological droughts, it's when we have a lack of a precipitation of available water from snow and rain. And when we talk about hydrological droughts, it's when we do not have a lot of dry for in a river basin. And for agricultural drought, it's when we do not have enough water for plant growing. And of course, if we have a very prolonged, long period of lack of rain, and it means reduces soil moisture, and this soil moisture limits, of course, the availability of water in our river basins and also for agriculture. So this the concept of drought at all, it's very complex, and we have like an addition of the effect of lack of rain and in an area, and it provoke as consequence on hydrological regime, but also on agricultural part in that area. And this effect, they translate in a socio-economic drought. So it translates clearly in a different, in a lack of resources, water resources for economy, for population and food production. In this way, we can add to the first three definitions of drought, the last one, the socio-economic drought. I'm telling that because it's very important when we want to work on drought and define the methodology to fix which kind of drought we want to address too. And this is what we have done in synergy with other scientists working in the project, but also with the pilots, the leader of the pilot that we have in the Germ of Life project, because of course we want to, the aim of the project was to produce something that is helpful to manage the road risk in the pilot area, in the Mediterranean area. And in this way, we know well that there is many different techniques, and of course earth observation play a key role in to detect for a big area the drought effect on vegetation. This is it's an example of a earth image, a satellite image. This is from a high resolution Sentinel data set, and in what tell us this image? This image tell us with different color of green what is the status of the vegetation. And in particular, the greener area are the area where we have more vegetation in a health condition, while the brownish, yellowish area are the area where we have dry vegetation. And the powerful of this, the remote sensing, is that we can cover large area, like a pilot area or bigger, using different using only one image. And this is very important because in a synoptic view, we have a lot of information, and it also reduces the monitoring at ground. So we do not have to collect a lot of information in the field, but we have this information already in our database from an image from a site. In addition, we can see that we have in the same area different overpass. So here there are two different images, like, oh my, I don't know what's happened. Sorry again. I don't know what's happened today to my presentation. It might be that there is some, wow. I don't know why, but anyway, I will do again in this. Sorry, but it might be due to the presentation mode. Let's do in, sorry, I hope that you can see anyway. And that's what's in this, what is very important that we can have, for instance, in the same area, different overpasses of satellite sensor. This is, it's an example of an overpass on in August at the beginning of the summer and in 2021, and here in the second image, it's an overpass for the same period, but in a different period, in a different year, in 2022. And as you can see, the color of the image passed from a green to a very to a brownish color, and it means that the area that before in 2001 were more with more healthy vegetation, in 2022 where there were dryness, they were dried, and from this changing in color, we can derive a lot of information, and we can use this information as a proxy of the behavior of the vegetation. And particular nowadays from different platform, and mainly from the European part from Copernicus, we can get many different proxy and data of the vegetation status. And here in this table, I listed some of the most important or most used in Earth observation for vegetation monitoring and drought monitoring status. And in particular, in the framework of the Germ of Life project, we started a review starting from a previous action, and it was from a previous project funded by European Commission, where all remote sensing indicators for drought monitor were tested in for different locations in Europe, and we revisit the use of this data in the Germ of Life framework. And from that, we arrive to define different type of indicator that can be used and can be helpful for the identification of droughts. This is the first outcome from our Germ of Life project, and in this table you see listed different indicator of proxy of vegetation status that are available from Sentinel-2 sensor. We decide to use the Sentinel-2 sensor because this is a satellite sensor that gives us the opportunity to have a very good, fine resolution of an area, because the pixel size of this sensor is about 20 meters. So it means that for one area we can have every 20 every pixel contain a description of the status of the vegetation in that specific area. And this is one reason why we decide to focus at the beginning on Sentinel-2, but another reason it's also because Sentinel-2 have an overpass time quite frequent, because it overpass every 5 days and it cover again the same area every 5 days. And this is also very important, because when we have, if we want to have a very dense monitoring of the status of the vegetation, we need also a lot of information, not only at spatial scale, but also a temporal scale to follow the evolution of the effect of drought on, in this case, the ecosystem. Another idea at the beginning why we choose Sentinel, it was also related to the fact that Sentinel contain different spectral bands, so different information that can be really linked to the status of the vegetation. Of course, it contains NDVI. As was mentioned before, Najota, we rely on NDVI. That is a very common and used indicator of greenness. From Sentinel, we have the opportunity to compute every 5 days at 20 meter of resolution, the NDVI. In addition, NDVI is also available from other sensors, and it was at larger scale, but that can cover very big area, and it's also used in the past. So the use of Sentinel and DVI, it's also due to the fact that it's a very known indicator for this kind of study. Of course, in our review, we go into the detail to order the analysis of other indicator that can be potentially used for monitor of droughts. You can see here there is this chlorophyll red edge index, green normalized different indexes, and different vegetation indices. These are also related to the greenness of vegetation, and they sense a bit more the changes in the biomass production of ecosystem. But anyway, NDVI, it can track well the development, the changes in color of our vegetation, so it can give us good information about the phenology and the growing of our vegetation, and of course of the effect of the droughts on our ecosystem. And but of course, we have a remote sensing. We have this kind of information from satellite images, but we have also other methods that can be useful to, I try again, useful to understand droughts for different regions. And in particular, we, in the Germ of Life project, we wanted to see how, if we can, if it's possible to combine indication from NDVI and satellite indication and other proxies that are much more related to the meteorological droughts, because they are based on meteorological variable. And one of the most used database for in Europe for monitoring the meteorological information, it's the it's the database from European Weather Forecast Center, and in this database it's possible to have a daily information on the meteorological variable, and for each pixel globally, it's possible to derive this information at 1 kilometer scale, more or less. And the good thing that from this database we can compute some indicator of meteorological droughts, and we can have a very long time series starting from 2000 until now. And the kind of indicator that we can compute, these are like SPI, that is the standardized precipitation evaporation evapotranspiration index. This is a normalized index that take into account the water that is from precipitation, but also the water that go back to the atmosphere from due to the evaporation, transpiration from plants and evaporation from soil. So this is from this data set, we also check the other indicator of droughts, like the simple precipitation index. But basically, since we want to try to link the vegetation to the meteorology and to have a more robust estimation of droughts in Germ of Life project, at the end we opt for the use of standards precipitation evaporation index, the SPEI. And later on, Leah and colleagues from Atos, they will present more about how this indicator SPEI and also Sentinel data are included in the platform. And it's very important because from this SPEI, we can get a daily estimation, monthly estimation, and we can also use this data to forecast the effect of drought in an ecosystem. All this data can be coupled with another important information that can integrate the information that we have from satellite and from meteorological variable, that is the soil moisture. Soil moisture, it's another important indicator of drought because of course, it tells us how many water is in the soil and available to plant for growing. And this data, we have this data from satellite imaging. We have at 1 kilometer a daily time resolution, but this data from satellite, the Copernicus dataset, the resolution of this data, sometimes it's not good enough, mainly when we want to really understand what happened for small ecosystem, for very for small area, and in what we want to do for in our Germ of Life project to really characterize the ecosystem in the pilots. And so we decide to use the Earth observation, to use the available meteorological data from European data sets, but we want also to improve our knowledge at the pilot site. So we decide to to monitor all parameters at each location, building up, sorry, again, building up a installing the flux, the station, meteorological station, and but these are this is an example for the pilot station in Portugal, and so for in each site we define an harmonized method for collecting the information. We have standard information and the data of radiation, precipitation, and the standard meteorological variable. But in addition, we add information and measurements of radiation. In particular, we here put a sensor to measure NDVI, and so to get near real-time information of greenness of our vegetation. In addition, these data are, of course, coupled with the integrated in the platform with the information of from the other Sentinel data from European meteorological dataset to forecast this information, the indices of drought in the future, and for characterizing characterize the drought in the area. And what is very important that we decide to apply a standardized method for monitoring of this variable in each site, and this is replicable in each site. So I'm sure that Professor Ayub and Sonia Bluton, they will tell more about the similar and the same setup in different sites. But what is very important that at the in situ level, when we decide to use sensors, mainly for the radiation, we have to take make some decision, because technically we cannot have all information for the of all spectral bands in this setup at the in situ level. So we had to check which is the most convenient information on a spectral reference to collect which site, and we again relied on NDVI, that it's a green vegetation information. It tell about the greenness of our site, and the NDVI, it's also collected at the site using the same spectral band of the satellite sensor of this in particular of center. So it means that we have at the site the same spectral information that we can get from Sentinel-2 NDVI data. That's important when we want to compare and scale up our information to a bigger area. So going into the last slide to my presentation, it's about what we arrived to define in Germ of Life after this review and the consultation with other partners and pilots, that we wanted to, at the beginning, to define really the agrometeorological droughts, to link more also the agriculture part to the meteorology, and so to look at the rain deficit and soil water availability. And at the end, we realize that due to the different limitation that we have from SAT data, that we have from a European data set and from other data, our focus is mainly on meteorological droughts, but this doesn't mean that we do not give information about vegetation status and agriculture, agriculture droughts, but it's just to be consistent with the definition that I gave you at the beginning. So that's why we do all this part, of course, because we want to pass from the monitoring to the action. We want to have at the end the project a warning system, and we want to have information about the vulnerability of our pilot area, and to inform stakeholders, local stakeholders, and that can develop a target strategy for the pilots, and of course this can help policy implementation. Thank you for your attention, and sorry for the presentation that it doesn't went very smooth. Sorry, thank you very much. And if you have a question, I'm happy to answer.
From your presentation, actually, I would like to ask if there are any questions for the participants to leave them in the chat box, and then at the end of towards the end of the seminar, in the QA session, we will discuss this further. But of course, if we have a pending question right now, we are free to answer it. So please leave any pending questions you have, or as we move along with our presentations, in the chat box. Thank you. So Thank you for the presentation on the comprehensive overviews. You have shown us how drought indices help us understand current conditions and long-term partners. So we now move forward from understanding the drought indicators to exploring how we can look ahead and predict the drought events. So our next speaker is Ms. Leah Duran, lead data scientist and hydrology research at Atos in France. Leah will present the forecasting models and analytics developed for the Germ of Life project, showing how they incorporate methodological data and machine learning techniques to predict drought conditions in the Mediterranean regions that we are studying. So, Leah, we're happy to have you with us. Please go ahead and share your screen. Thank you.
Thank you. Let me share my screen. Okay, can you see it here properly? Can you see my screen full screen? Okay, perfect. So, good morning, everyone. So I'm Leah Duran. I'm working within Atos, which is an IT company based in France. And my team is in Montpellier, and we are working on machine learning applied to the hydrological cycle as a wide interpretation. So here is just the map with the different partners from the project, and you can see in yellow the 4 pilot sites that have been discussed by Manuela and will be also presented a bit later on. And our location here is in southern France. So just to give the general scope and where do the forecasting models fit in, the Germ of Life project has like 3 main sub-platforms, 3 main pillars. So there is the first one that is the drought characterization and also drought prediction. That is a tool within the platform so that we can understand the current situation and also adapt to any risk of drought that is coming. Then there is a vulnerability assessment tool to understand what is at risk within the territory, more specifically given the socio-economical conditions, for example. And finally, there is a last pillar that is providing a list of nature-based solutions for each territory, depending on their needs, to increase resilience towards drought in the territory. So as Manuela explained, there is a wide range of indicators to assess droughts. They kind of look at different parts of of the impact of drought. So based also on CMCC work and on workshops with other project partners, there was this first selection of indicators that were relevant to our project. The first one being standardized precipitation evapotranspiration index, or SPEI, that is focusing more on the meteorological aspect of things, so how much water will really be available or not for the ecosystems or the agricultural systems. Then there is a second one that is based on remote sensing information or from sensors information, also described previously. So this one is NDVI, so normalized difference vegetation index. It reflects more the stress of the plants of the vegetation. Finally, there is a third one we've also worked on so far, that is kind of a mix between the two, that is reflecting the stress of the crop water stress index, and also relying on evapotranspiration and different fluxes. And finally, also with the CMCC and University of Patras, there was a definition of a drought hazard index based on analyzing as well the frequency of past droughts on a given pilot site. And this one is for now relying on SPEI, but might include other indicators as well later. So then what do? We have these indicators, and we're interested in knowing what is going to happen in the future. So when we are talking about the future within the scope of this project, we are working at seasonal scale. So that means we want to know what's going to happen over the next months. We are not looking at long-term effects of climate change. We are really looking into the next months. So machine learning is like when you train algorithms from long data sets, so that can detect the underlying variations within the data. And that's the way the machine learns. So basically we detect current information within the data, and that enable us to then forecast what is going to happen based on what was already existing in the data. So in order to do that, we use a lot of different data. That is a key when we talk about artificial intelligence and machine learning. So part of the information is coming from remote sensing information from satellites. And in our case, it's Sentinel-2, and more specifically for the NDVI information. So that way we have an historic starting from the 1980s, roughly. For the other information, as we didn't have stations installed before the beginning of the project, in order to be able to forecast drought conditions based on like a large data set, we needed historical data. So in order to get those, we are using existing data sets from Copernicus, that is called ERA5 Land. And it's like global models, physical models using equations. And they provide, for example, temperature and precipitations since the 1950s up to now. So then we can compare this data with the data we actually measure on the pilot site with a meteorological station to validate or at least assess the difference between these generated data set versus measured data. And we're able to then train the models on that large data set. So obviously we use then the data of the ground station, of the meteorological station, both to understand the difference between historical data set versus the measured data. And also then it's to monitor the behavior of the model. So when we forecast an indicator, when we forecast drought, we can afterwards, once the data starts coming in from the station, assess the performance. Was the prediction good or not? And from there, we can decide if we want to improve the model or if it's fine, it's working well, the error is low, and we keep it that way. And finally, the last part of data that we need is a weather forecast. That means we need to understand what are the expectations in terms of temperature and in terms of precipitations in the next months to come. So this data is provided by the expert center, also with a large physical models. So from ECMWF, and it's integrating both the expectations in terms of circulation, but also, for example, if there are some El Nino events or things like that, so that we can have an expected variation in the exact location of the sites. So that enables us then to forecast up to 7 months ahead the mentioned indicators. I added a map here, but for now we are working at super small scale in terms of forecasts. But the idea would be then to be able to scale up, and what we do on just like a single coordinate to extend it to larger areas in the future. So that's what I was just explaining. We have this kind of like different 3 main layers to be able to understand what is going to happen in terms of drought on a specific location. We have historical data, we train the model, and we have then the model that is ready to use to forecast, but we also have available for the users on a specific territory the past drought conditions. That is interesting to compare what you are expecting. Is the drought that is forecasted for next summer will be as intense as the one in 2022, for example, or less. So it's also useful to have these historical time series available. Then you also, through the platform, have the information on what is the current status of drought or not drought on your site, because we have the measure on the ground station. So thanks to the measure on the ground station, we can compute the SPI, so the meteorological drought, and you know the current value. And you have also the measured NVA, so you also know the stress of the vegetation. And finally, you have the forecast, thanks to this initial forecast for weather conditions, then we can deduce the drought future conditions. So that's what we've been doing on the 4 sites of the project. So we have all the historical information and the model that are calibrated on this different information. Then we are also able to compute each month automatically the drought conditions. And then finally, we have the forecast. So how does it work technically? We have stored, so for SPEI, it's not really machine learning. It's actually, we have an equation that is enabling us to calculate SPEI. There is a statistical fit where you can store the parameters for these specific sites. And these statistical fits then enable us to compute for the real time, near real time each month, but also for the forecasts. So then what do we do with that information? It's all going to the database of the project. And in the end, it will be displayed on the dashboard for each site, where you have the historical information, you have the forecast and the current condition under the form of a graph that is showing that, and also in the case of NDVI as a map from remote sensing, from satellite information. For crop water stress index, it's not yet deployed in prediction, but we've also been working on it. And here is an example of, I think it was a reverse in terms of the legend, but never mind. There is the possibility to compute it from ERA5 land data, and CMCC had some pilot site installed previously on a longer time period that enabled us to actually compare and assess the difference between the ERA5 dataset versus the measured dataset to validate the approach. And finally, for NDVI models, so here it's like really machine learning forecast. We started from very simple model, like basic regression models and simple artificial neural networks on the raw signal that was quite noisy. The idea was also to identify what were the most contributing variables to be able to forecast NDVI. So obviously there is like precipitation and temperature are playing a big role, but there is also the soil temperature that is relevant, the water content of the soil, and the surface efflux that are major contributors to the forecast of NDVI. And so finally, on top of cleaning a bit the signal with the adapted filters, we have managed to have so far a forecast that has quite a high performance and a relative low error on the site of the project. So here it's an example on the Spanish coordinates. And so similarly to the SPEI process, we have this part where we retrieve remote sensing information to be able to have a long historical data set that enable us to train the machine learning model. And then the parameters of the model training are stored so that we can forecast using this time the seasonal forecast from ECMWF. And this is then to be written in the database of the project to be visualized into the dashboard. So that's the rough data flow and explanation on the forecast process. So feel free to ask any questions you want if you want more information, or to get in touch by email as well.
Thank you, Leah, for this second presentation and for showcasing us your sites actually showing the importance of combining historical data, reanalyzing data sets and forecasting tools to anticipate our conditions and support timely decision making. So again, if there are any questions, you are free, participants, to put them in the chat box or the Q&A box, and we will answer them. We'll try to answer them as best as we can during the QA session. So we will now move forward to the pilot demonstration that we briefly discussed in the introduction. Let's just put it on the screen. We will now move to part of the demonstration of measure, where we will see how these tools are applied in real environments at some point. So for our first demonstration, we have with us Professor Athanasios Sergiriou from the Laboratory of Atmospheric Physics at the University of Patras. That is also the lead partner in this project. So Professor Sergiriou will present the Greek pilot in Aegelia, explain the environmental context and the monitoring system installed and the first observations collected so far. So Professor Sergiriou, the floor is yours. Thank you.
No, thank you.
Sorry,
Yeah, sure, please.
if I interrupt
Go on,
you
Manuela.
just 1 second, just because I have, I have to leave in few minutes. I have to leave the meeting, but of course I will try to join maybe later on before the end of the meeting for if there are questions. But anyway, you can reach me by email, and I will be more than happy to answer to your question if any. Thank you. Sorry.
Thank you, Manuela. Thank you. So, Professor Sergiriou, if you can go ahead and share your screen, you should be able to.
No, apparently, Léa vous me bloquez.
Yeah, you're still sharing. Please stop in order to let Professor Sergiriou proceed with his presentation. Thank you.
Sorry, do I need to do something?
Yeah, you're still sharing your screen.
I'm still sharing it?
Yeah, I'm seeing the Atos logo with
yeah.
Sorry.
advancing what matters. And I'm not allowed to share my screen.
But I'm not seeing how to stop it. So.
Panagiotis, look at you as a host.
Yes.
Yes, let me check maybe.
Okay. I figured it out.
Great, thanks. Now it works.
Yes, by sharing mine. So, yeah. So you go ahead. Thank you.
I hope you can see everything. So hello again. Thank you for being here. I'm presenting briefly one of the components of the Germ of Life tool. What we are producing is a vulnerability assessment tool, which is being built based on what Ms. Durand presented you previously, and what also Manuela presented regarding the general context of the tool. But one of the core elements of this project is 4 pilot projects, one in Greece, a second in Italy, a third in Portugal, and the fourth in Spain. I'm referring to the pilots by alphabetical order. I think that the Greek pilot was the first one installed. It's already operating for about a year now. It started operating on December last year, but we have clean data from the 1st of January this year. The position is in a city nearby Patras called Aegion, but not close to the sea. It's up hills at an altitude of 800 meters approximately. The ecosystem there is vineyards. The coordinates, you can see them on the screen. There's also the link the site via Google Maps. Panayota, I don't know if we will be sharing the presentations at the end of the webinar. I mean, so you can use this link to get further, a more detailed glimpse of the site if you wish. Here you can see again via Google Maps the itinerary you have to drive from Patras here from the university to the location where the pilot has been set up and running. Okay, here's the exact position of the meteorological station of the pilot is here. The pilot is all this area. The radiometers of our pilot are viewing this specific piece of land, but there are vineyards all around this place. You can have an overview via this picture. It's vineyards, and the main species of vine cultivated there is one called Syrah in Greek, or I've seen this being spelled out as also Shiraz. I don't know if you're wine specialists. I mean, the wine specialists may know that, but we are going to have very interesting details later on by Professor Kundras, who honored us with a presentation today. Moving to things I know better than vineyards, the instrumentation of the station, the basic instruments are what we measure is air temperature and relative humidity, wind speed and direction, precipitation, the photosynthetic active radiation, the normalized difference vegetation index. This is something that we need to validate with the Sentinel measurements that Professor Balzarolo and Ms. Duran told you before. And also we are measuring the soil temperature and the water content with special sensors at 3 depths, 25, 45, and 65 centimeters. I would like to stress that this configuration is the same for all of our pilots to be able to allow us to have direct comparisons. I'll provide you some further details about the sensors. This is the HC2A is the relative humidity and temperature sensor. It is shielded as it is mandatory for all sensors of this type being in the field. We use the Davis 6410 model for wind speed and direction. The 300 0.3 rain gauge instrumentation is the tipping bucket instrumentation. The photosynthetic radiation sensor is on this at the edge of this boom. It's the green sensor shown with the arrow. The other two sensors are the radiometers used to measure the normalized difference vegetation index. They measure the incoming radiation and also the radiation that is being reflected by the vineyard. The combination of these two values via a specific formula provides the health of the plant, which is viewed by the sensor at the bottom. You can notice that the sensor has been positioned in a tilted. It's not directly looking the ground, but it's tilted to ensure highest view angles, solid angle of the vineyard, which is just in front of this boom. Okay, oops, sorry. Yeah, unfortunately, I couldn't find a picture of the relative humidity, I mean, of the sensor measuring the ground temperature and water content. This is the type of the sensor anyway. We have three kinds of sensors like this installed at 3 different depths, as I told you. All signals are collected in data logger. We use the Campbell scientific model CR1000X. In this specific pilot, we are able to have a power. I mean, the data logger and the weather station is supplied by the mains, and we also have a surface line internet connection, which is very, I mean, it's more reliable compared to Wi-Fi connections. So we haven't lost any data within a year of operational, almost a year. And here you can have the overall overview of the weather station, the instrumentations, the wind and speed direction and gauge, rain gauge, the temperature and relative humidity, the radiometers at the edge of this boom. This is the vine. Sorry, it's a picture during winter, so there are no leaves, but believe me, during summer this is getting very green. And in this box, it's the data logger together with all the electrical, the wiring necessary for the operation of the plant. So the data are continuously transmitted and we can have access. I mean, all the stakeholders, because we are already in contact with the stakeholders in the area. So all the stakeholders can have, the interested one can have access to the measurements via a smartphone application developed by the manufacturer of the data logger. You can see an example on this screen, the temperature at a specific date, relative humidity, wind direction, speed, rain, etc., etc. But there's also a web desktop application through which we can access the measurements and select. Sorry, it's in Greek. Here's the daily precipitation, the monthly precipitation, the annual precipitation. We can also have graphs, but not only for precipitation, but of each and every parameter that is that we are interested in. An example of graphs for a specific period. This is a graph for the temperature. We have also some simple statistics for the period shown illustrated on this graph. And yeah, I think this is all about the Greek pilot. It was fast, but I mean, I think the essential has been presented. Thank you very much for your attention.
Mr. Argyriou, for your presentation, and of course, it was a great presentation because we had a first look on the Greek pilot site, and most of the partners will be able to see this pilot site in person in our final meeting at the end of the project. So we have a bit more time to see it in person, but I hope everything will be to their satisfaction. So let's move along.
Excuse me, I forgot to mention that we have a few minutes video presenting the pilot, but I don't know we have enough time. Perhaps we can
at the end, if you wish to. Yes, and we can move along now with Ms. Appleton, and then we can show it in the end. So our next speaker is Ms. Sonia Appleton from the project manager at Lamoro Development Agency. So Sonia will introduce the Italian pilot located in Le Vallere Park. I hope I pronounced it right. It's a unique ecosystem facing both drought and extreme rainfall challenges. So she will share how the pilot is progressing and how they are engaging the local stakeholders and the information on the local side. So Sonia, the floor is yours. Thank you.
Thank you very much, Panagiota. Can you hear me and can you see my presentation, my full screen?
Yes, thank you.
Okay, thank you. Thank you. Good morning, everyone. I'm Sonia Appleton, and I represent Lamoro Development Agency, the Italian partner of the Germ of Life project, involved in particular in the implementation of the pilot action. And in this presentation, I'm going to introduce the Italian pilot area, highlight the partners involved, and share the actions we have implemented so far. And first of all, I would like to introduce the organization I represent, so you can have a clear picture of our role and the contribution within this project. Lamoro is a development agency based in Piedmont region in the northwest of Italy. It was founded in 1995 as a consortium bringing together more than 40 municipalities with the goal of improving the socioeconomic opportunities of a large territory by promoting, first of all, its local resources, identity, and potential. Our mission at the local level is twofold. First, we work to implement sustainable development strategies that actively involve public and private stakeholders as well as local communities. And second, we focus on responding to local needs, taking into account the specific characteristics of each territory and each municipality we work with. And in the Germ of Life project, we work closely with the management body of the protected areas of the Piedmontese Po, which is not only the associated partner in the project, but also the authority responsible for managing the Po River Park in Piedmont, for Piedmont region. And their work is deeply influenced by the Po River itself. All the areas under their management are shaped by the presence of the river. The Po River is the longest river in Italy, running for more than 600 kilometers, and it originates in Piedmont and flows eastward across 4 Italian regions: Piedmont, Lombardy, Emilia-Romagna, and Veneto. And the Po Park oversees the protected areas along the Po River. This authority was established by regional law, and the authority plays also a crucial ecological role. It links the Alps with the Piedmont Plain and with major urban centers like Turin and Moncalieri, creating a key ecological corridor that supports wildlife movement and the continuity of natural habitats. And all its landscapes include riverbanks, wetlands, woodlands, and also agricultural areas. And all these areas contribute to biodiversity, recreation, and also sustainable land management. A key hub within the park is Cascina alle Vallere, which plays an important role in education, conservation, and also environmental awareness. The urban park stands within the Piedmontese Po Park. We have identified a specific natural area called Le Vallere Park. This park covers 130 hectares and sits at the meeting point of the Sangone Torrent and the Po River, mainly in the city of Moncalieri and partially in Turin, which is the capital city of Piedmont region. This is a true natural retreat right in the city. Here, biodiversity thrives, and every visit feels like a small escape from the urban life. It's perfect for walking, cycling, or simply enjoying the fresh air. What makes this urban park truly special is its mix of uses. There are spaces for sports, spaces for recreation activities, but also meadow areas carefully maintained by farmers who handle mowing and upkeep of agricultural areas. On top of that, the park is a part of the UNESCO Collina Po Biosphere Reserve. That means that this area is recognized not just for its beauty, but also for its ecological and cultural value. The Biosphere Reserve includes the protected areas along the Po River, the Turin Hills, as well as wetlands and forests. And this area promotes sustainable development and environmental education, serving as a sort of model for how cities, farmland, and natural areas can coexist in harmony. Here we have some images of the Le Vallere Urban Park. As you can see, this park combines green spaces for recreation with natural habitats that support local biodiversity, and this photo will give you an idea of the park's layout and its vegetation. For this project, a specific area within Le Vallere Park, within the urban park, was chosen as a pilot site, and the pilot site is located within the Phenological Garden. Within this area, the meteorological station planned by the Germ of Life project was installed in September 2025, last September this year. Why was this site selected? The site was chosen for, first of all, for its significant ecological importance, for its significant ecological importance due to its high biodiversity value. Specifically, it consists of very special meadows, meadow areas, rich in plant species, which have been included among the donor sites of the Piedmont region. It means that these meadows have been already used for seed collection, and these seeds have been employed or can be employed to revegetate or restore natural habitats or degraded areas, even starting from bare soils. The collected material, the collected seeds are of high quality and demonstrate strong adaptability and resilience to environmental stresses. This ensures the long-term survival of new plantings and contributes to enrich the meadows in terms of biodiversity. And monitoring the negative effects of climate change and especially of drought on these species, on these seeds, is particularly important for the park itself, as events such as droughts could favor more hardy and often exotic non-native species, which may threaten the original composition of the meadows and their biodiversity value. Like I said before, the pilot weather station was installed last September, and as already Professor Giriou told before, the pilot weather station measures these variabilities, for example, meteorology, temperature, humidity, precipitation, dew point, vapor pressure, data from soil, water content, salinity, temperature, permeability, radiation and vegetation, for example, solar radiation, NDVI, and reflectance. These are the specific parameters which are measured by the station: atmospheric parameters, total precipitation and maximum intensity, air temperature and relative humidity, dew point and vapor pressure, soil parameters, volumetric water content, electrical conductivity, soil salinity, soil temperature, permeability related parameters, and also radiative solar parameters, photosynthetically active radiation, solar radiation, NDVI, the vegetation index, and the reflectance. These are common to all 4 pilot areas in the Germ of Life project. Within this project, stakeholder will use station data and digital tools, which are produced by the Germ of Life project to design and implement actions which foster biodiversity conservation and improvement of ecosystem services. We are a local development agency, and with the Po Park Authority from the beginning of the project, we started to involve several stakeholders, private and public stakeholders, for example, farmers, local authorities and the planning bodies, universities. For example, in this project, we are cooperating, and we will cooperate in the next months with the University of Turin, which are implementing another project funded by the European Agricultural Fund for Rural Development on seeds biodiversity on meadows. And our aim is also to involve the community itself and the citizens itself. They are called to participate in conservation initiatives, and we would like to raise awareness and support sustainable practices. I think it's all from my side. Thank you very much for your attention.
Thank you very much, Ms. Appleton, for this informative presentation. And it is extremely valuable to compare different regional contexts and see how the project's tools are being adapted to local needs. So as we mentioned, we are pretty much using the same equipment through the various pilot stations, but we are dealing with different environments and different stakeholders involved. Now we will move to our keynote address, and it is actually a stakeholder from that we have first encouraged in our dissemination in our pilot area. It's our keynote today will be delivered by Professor Stefanos Koundouras from the Laboratory of Viticulture at the Residential University of Thessaloniki in Greece. So Professor Koundouras will speak about the climate crisis in the Greek wine sector. And focusing on the case of Aigalia, as mentioned, it's the Greek pilot site, a region directly relevant to our pilot. So thank you very much, Professor Koulouras. We are honored to have you with us. Please proceed with your presentation.
Thank you very much. Thank you to Professor Argyriou for inviting me to this webinar. It's an honor for me to participate and to share my experience in the study of climate change in the Greek viticultural areas and the many effects that has had so far in the wine industry of Greece. So I load my presentation. It's a little bit slow, forgive me. Okay. Okay, everybody sees the presentation?
Okay, thank you.
Yeah, it's perfect, yes.
Yes, okay. So, first, now the issue of climate change in the wine world, in the wine business and the wine research has been divided into two phases. In the first period, which started in the beginning of the 2000, the main issue for the Greek for the wine industry in general was the change in the shifts of harvest dates to earlier dates, which meant that the harvest of grapes was situated in periods of the year much more hotter and warmer than usual. This prevented the grapes of reaching their, let's say, best expression because the conditions, as we will see further on, were not the ideal in this period. So the hotter the conditions of the year, the earlier the harvest, and this made the wines lose some or much of their typicity. And typicity is important, especially for wine grapes around the world, especially for the best-known wine grapes like in Piemonte or in some areas of France, Italy, Spain, and Greece. So this period was changes in the phenology of the grapes, but within the normal, let's say, normal borders, normal values of climatic parameters. But then, meaning the last 10, 15 years, we have passed to more extreme conditions, and then the results are much more severe than in this first period. So I will divide my speech for these two periods, and then I will talk about some adaptations of the wine sector. Now, the viticulture is being a cultivation in the most mild climates, which means that the isotherms of grape cultivation is 13 degrees north in the northern hemisphere and 24 degrees south in the northern and the opposite in the southern hemisphere, which means that these are not values of absolute necessity. These are the conditions for the ideal, the best quality production of wine grapes, which means that in higher temperatures than 24, the vine can still survive, but does not produce grapes of great typicity and great character. So we've seen this area progress towards the poles in the northern hemisphere and the same to the south. And in the years that have passed, we've been moving slowly this area to the north in the northern hemisphere and to the south in the southern hemisphere. And now the projections, according to the RC4 climate scenario, is for approximately 500 kilometers movement, displacement of this area towards the north, which means that, let's say, Greece, which is one of the southest areas in Europe, is practically put outside of this ideal, let's say, window, geographical window. We have done a thesis with Georgios Koufos which studied all the grape growing areas of Greece, or the major grapevine or areas of Greece, for the 30 years between 1980 and 2010. And we have seen that during these 30 years, big increases in temperature, especially the nighttime, the lowest, the minimal temperature of the day. This is the blue bars, and the reds are the highest temperatures of the day. We have been seeing increases, especially for the nighttime, which are of an order of approximately 2 to 2.5 degrees during this period. And you will see in this table that, especially for the second column, which is the mean, the mean of the minimum temperatures, all of these trends are significant, which means that these are trends that are very important, less significant for the maximum temperatures, but for the minimum, all the regions showed a very significant trend towards higher temperatures, which reached approximately 2 to 2.5 degrees only in 30 years, which is huge. To see some examples, for example, in some areas in the north of Greece, in Kavala, for example, we have seen an increase of 1.9 degrees in 30 years, in Nausa 2.1, if we compare the season temperature, which is the 6 months of the growing season. If we take into consideration only the 3 summer months, it's 2.1 and 2.6 for the same areas. Is the increases in nighttime minimum temperature. So the average of the growing season temperature is becoming hotter and hotter, and the projections for the last 40 years of this century will be that practically all areas, or most of the areas of Greece, will be classified beyond the 24 degrees, which was the hottest isotherm, which means that all of the areas, or most of the areas, except for some very mountainous areas of Greece, will become not proper, not suitable for quality viticulture. Now, what temperatures got to do with the vine? A lot is the answer, and first of all, it interferes in all developmental stages. We see here from a study in Piemonte done by Tomasi that all the major developmental stages of the vine, the budburst, the bloom, the rhizome, are very closely related to temperature, which is the mean temperature of the growing season, especially bloom, which is the most central and important stage of vine, of berry development, grape development. This, of course, leads to, as we saw in the previous, that the higher the temperature, the earliest the occurrence of these stages. And this projects the same into the harvest time, which shifts towards earlier days, which sometimes reaches approximately 1 month compared to the previous century. Why is this important? Because for each variety, there is a window, which is the perfect window. This window is situated around September. The month of September in every area of the world is the ideal for harvest because temperatures are mild, and this corresponds to the best conditions for the grape biochemistry to develop all the aromas and flavors that afterwards reach the wine. So as the harvest dates become earlier, this window is lost, and grapes practically ripen during a very hot period of the year, which is end of August or beginning of August in some cases. So if we lose this very important time window, which is around mid-September to mid-October, which is the ideal in every area producing quality wine grapes, we lose the potential of producing good and typical and expressive grapes to produce quality wines. This, among all, is because we lose the synchronization of ripening between the different berry tissues, the juice and the seeds, and most of all the skins, which contain the color and the aroma compounds. Here again, the same two areas, we see that for Kavala, we have for Sauvignon, which is a variety very known in the world, 5 days earlier harvest. In Assyrtiko is the second. This one is a Greek variety named Assyrtiko, very well known, cultivated mostly in Santorini, but this is from vineyards in the north of Greece. Assyrtiko is harvested earlier, 16 days earlier. If we go to Cabernet Sauvignon, 23 days earlier, and Agorgitiko, another variety from the south of Greece, 18 days earlier. So it's real that the harvest is happening much earlier. Now, so this all loss of synchronization, losing typicity, and also we have a compression in harvest time, which means that the grapes, it's a logistics problem that have the wineries. Grapes arrive all together because they ripen very quickly, and they cannot satisfy the need for volume in the cellar. So they have to adjust the harvest not according to the best quality or the best ripening, but according to the capacity of the winery, which is also a very big problem to produce quality wine grapes, which have to be harvested at a precise maturity. Now, especially for the secondary metabolites, which are the metabolites that give the aromas, the typicity, the flavors, the aging potential, like anthocyanins, we have seen that we know that temperatures higher than 30 degrees decrease their formation, their biosynthesis. And for aromatic compounds, the compounds of the aroma, the volatile compounds, this is much lower. They are very more sensitive, and practically at temperatures higher than 18 degrees, we have much less aroma, especially if these temperatures, the high temperatures happen at night. So high night temperatures, as we have seen before, are crucial, are responsible for the lower aromatic quality of the grapes harvested today in many areas of Greece and in the world. We've seen the same in the wines. We've seen that the alcohol is increasing. We know that the alcohol is a problem for wines now because there's a huge campaign against alcohol, which touches the wine industry. And now alcohol, because of climate change, is increasing. This is a big problem for wine producers. And one of the biggest concerns is how to decrease this alcohol in the wines without decreasing the overall quality, of course. And this is the point where the grapes have a big, let's say, potential of adaptation, is the fact that the grapes have a number of varieties, which is very big. We are talking about thousands, at least 5,000 varieties cultivated in the world, each one of those having different climatic needs, different climatic suitable conditions. So we can adjust areas to the grape varieties, or the opposite, the varieties to the areas. So we're talking about the topo variety or the topo cultivar. This must be together joined to have the best adaptation to climate change. And the best way to adapt to climate change is by changing varieties, because there is always a variety which is suitable even in conditions very hot, like the Greek varieties, for example, are very suitable for hot areas. And so these varieties will be very interesting around the world in the future as the climate is warming and the wine producing areas become warmer and warmer. Greek varieties will be of great interest. So how do we know which is the ideal temperature for the varieties? This is by tasting of the wines. Each area producing quality wines has some wine tastings which are done by the local authorities to define the quality of each vintage. So in every big area, wine producing area of the world, we have these wine tastings done by professionals which define the quality, the overall quality of each vintage. And so we know that, for example, if we correlate this to the temperature of each year, we can have a curve like this one, which has a point which is the ideal for the ripening and the quality of the grapes and the wines of this particular variety in this particular area. And so what's happening to these grapes now? There are areas where this maximum value, the ideal value, is becoming greater. And in other areas, like in greater than the projected ideal value, like in Rioja. In Mosel, for example, where we see that the ideal is 13.9, we are still at 13.4. So areas which are practically, let's say, more cooler areas have still some time to adjust. And for the moment, most of them, or at least some of them, are being favored by this change of the climate. But in most areas of the southern part of Europe, like Spain, Italy, Greece, Cyprus, this variety, which is here, you see 17.5 for Rioja in Spain, it's already, by the end of the 2000th century, it's already surpassed. It's 18 degrees, and it's now even higher because we're 25 years later. So we're going to see more of this, and these areas are very important because they have a limit in legislation about which variety to cultivate. So we cannot change varieties as easy as in other places because these are very important and areas of great cultivation. Now let's come to the second part, which is the more recent evolution, which has to do with extreme conditions, extreme temperatures, extreme heat, and extreme drought. We've seen here, let's say, number of days of temperatures, nighttime temperatures higher than 20 degrees is rising. Likewise, but not so significant, the number of days with temperatures superior than 30 and 35. There is no real significant trend, but we see here in some areas of Greece there is a trend, significant trend, in some others not. But generally, we increase the days of with extreme maximum temperatures. This leads to some problems like sunburn. Sunburn is because the grapes have a protective layer of waxes on their surface, which is destroyed by higher temperatures. And once this happens, then let's say the epidermis of the skin is much more vulnerable to variations of temperature, especially if they're exposed directly to the sun. So this kind of sunburn damage is very common in the last years in Greece and other places. Here we see lower damage or drying of the grapes, like in the photograph in the right. Also have dehydration, which is very important because as respiration increases in the grapes, this leads after a moment to the death of the cells of the grape. And when this happens, all this compartmentation that exists in the interior of the ripening berry is destroyed, and the water can move freely from and toward the grapes. And so what's happening is that the water flows backwards to the plant, especially if the plant transpires has an intense transpiration. And we see this dehydration very early in the season. It's not a dehydration which is normal by the end of the season. It's a dehydration early in the season when the grapes are not ready to harvest. So this is a grape which is not good for harvesting. Or we can see all things happening together because actually all these abiotic stresses are happening at the same time. Color degradation, we have seen that anthocyanins are very sensitive to temperatures higher than 30 degrees. Actually, in temperatures like 35 or 40, they are denaturated and they are decomposed. This means that the color is decreasing, not the synthesis of anthocyanins doesn't stop, but it actually the anthocyanins start to decompose. The same is at even more significant problems in the white grapes, which do not have the protection of the phenolic compounds which are present in the red grapes, and they form these color compounds which are not very good in white wines, as you understand, because they are called the early browning of white grapes and white wines, which is also a very big problem for the hot areas. But the biggest problem in these areas will be drought. We know, of course, that water is the largest, agriculture is the largest user of water. Irrigation needs are increasing, but the water resources of the world are decreasing. So we have to manage this problem. And the water movement, the water situation of the vines is not entirely a climatic issue. It's also a matter of the soil of the plants. The movement of the water is transient in the plants, which means that it goes from the soil to the leaves and then to the atmosphere. But there is a biological factor there, which is the stomata, the movement, the opening and closure of the stomata of the lower side of the leaves, which means that the stomata open to let the CO2 for photosynthesis. But when conditions become very difficult and drought increases, then they close, which means that they limit photosynthesis. When the stomata are open, water is transpired by the plant through the stomata, depending on the conditions of the atmosphere. And these conditions, these conditions are temperature, solar radiation, relative humidity, and wind speed. All of these define what we call the evapotranspiration, which means the loss of water either directly from the soil or through the plant by transpiration. On the other hand, this is the demand. So if the plant can cover this demand either by the rainfall or by the stock of water in the soil, which also depends on the depth of the root system, then we're okay. But if this starts to become deficitary, which means that the water in the soil or the rainfall cannot cover the big demand of the atmosphere, then we enter the point of water deficit in the beginning and then water stress, which means that first photosynthesis declines because the stomata close. But the most important thing is that the temperature of the leaf rises because transpiration is also because the evaporation, the passing of the water from the liquid to the gas condition absorbs energy from the atmosphere and cools the environment. This cooling is very important for the leaves to sustain the high temperatures. When stomata closes and transpiration stops, then the leaves start to heat up. And another problem is also the energy from the sun, which is the energy for photosynthesis, can become also toxic to the plant because it cannot absorb this energy, and the surplus of this energy becomes toxic and can create big problems. So it's actually a very complex phenomenon where temperature, solar radiation, and humidity enter into this complex phenomenon. Now the actual problem of drought depends on the timing of its of the timing of the occurrence of water stress and the level, of course. So the earlier in the season that that drought appears, the higher the problems and the damages in the production and the quality. In the beginning, we diminish the quantity. The latest the apparition of water stress, the more the problem is for the quality of the grapes and less on the quantity. But as this can happen every year by year, and this diminishes the reserves of the plant, then even the sustainability of the vinegar and viticulture can be questioned. So this is a typical image of a plant where we have multiple stresses. We have a heat wave where we have heat damage on the grapes. We have drought damage. We have photo inhibition from solar radiation, which actually every stress happening at the same time. Now, let's go to the last part, which is how this, how the sector in Greece and other places. Let's take Aialia, for example, as an example. How this the sector can adapt to these conditions. If we can adapt, then what are the best or the most common ways of adaptation? So this first is some very beautiful photos of Aialia region, which is one of the more beautiful in Greece. As you see, vineyards in high altitude near the sea. And the typical variety of the area is this Rhodhitis grape. First of all, if you see here in the heat requirements of the grapes cultivated in Greece, most of them are Greek, but there are some international like Nebbiolo, Cabernet Sauvignon. But you see that the most of the varieties cultivated in Greece, among them Rhodhitis, which is the variety cultivated in Aialia, has one of the highest heat requirements, which means that these varieties adapt well to hot conditions. So regarding the first part of our talk, Rhodhitis is a variety that can go very well in areas which are becoming, where harvest is becoming earlier and earlier. It's one of the characteristics of the Greek varieties, which will be very interesting in the future for many countries. But there is not only this. Greek varieties have, most of them, a better adaptation to drought and other abiotic factors. You see here, like Agorgitico is a very well adapted variety to drought, because in the xylem, the xylem tubes and the leaf stomata, we see here that compared to Xynomavro, which is a variety from a cooler area, we have more and smaller xylem tubes, and we have smaller number of stomata in the lower surface of the leaves, which means that it is a genetic factors that limit or control better water loss compared to a variety from a cooler environment like Xynomavro, which is not so well adapted. And this is classic for many Greek varieties. Xynomavro is actually the odd one out. Is all Greek varieties are mostly like Agorgitico. Aialia also has the advantage of being in a high altitude area, and of course high altitude is one of the most common adaptations when temperatures rise, because as we go up in altitude, we have lower mean temperatures, we have higher humidity, we have more global radiation, which is in most parts favorable for the grapes. When radiation that is not happening at the same time with high temperatures is mostly favorable and suitable for the production of quality wine. So altitudes is one of the ways to adapt to future global warming conditions. But the grower also has a lot of options. There has been a lot of research in most parts of the world where climate change has been is important the last years. And we've seen many methods to control to decrease the problems created by climate change, like, for example, the quick rise in sugar, which leads to very high levels of alcohol, as we said, which is a big problem. One of the ways to overcome this is late removal of active leaves of the plant at the top end of the canopy, which can slow down the sugar accumulation. In that way, harvest the grapes at a good maturity, but not very high potential alcohol levels. Delayed pruning is also an option, because here is an experiment from Italy, and we have seen that in the plants which are delayed at pruning, they are at the same time at a very early stage of development. So this leads to putting back the temperature of harvest to a more normal, let's say, normal period. We're going from August back to September. We're trying to push the harvest back to September, which is the ideal month. And this is a way to do it, is to prune the vine as late as possible, because that's, in this way we push the whole vine cycle towards later season, and we can, let's say, overcome partially maybe the problem of the earliest harvests. Irrigation, of course, is a big question. What we do with irrigation, it's a big issue, not to discuss here because it is very complex issue in many, but the irrigation pipelines are becoming more effective, like this is direct routes on irrigation, or sprinklers, which, because of the operation of the water, as I said before, apart from increasing the humidity of the soil, they alter in a positive way the environment, increasing the humidity and cooling the canopy, like in transpiration, as we said before. Of course, the use of other sources of water or water containers. Changes in the canopy in order to expose the grapes as little as possible to direct solar radiation, which means increase in temperature as well, or changing the canopy systems to more sprawling canopies and not vertical developed canopies, which expose the grapes to the sun, which was the idea in the beginning, but now we're trying to do the opposite. We're trying to cover the grapes as much as possible. And using artificial nets, which are also very used in this lately, changing the orientation from the classic north-south to east-west, which does not expose the grapes directly to the sunlight. East-west is preferred today compared to the classic north-south orientation of the rows. The spraying with some compounds like kaolin particles, which reflect the sunlight. Try to adapt the plants to the soil and create a deep rooting system by slow initial vinegar growth in order to favor, let's say, a deeper root system. You see here a vinegar in Greece in an area, not irrigated area, which during the very hot harvest of 2023-2024, it was perfectly okay, but you see how deep the roots go. This is a vinegar in Santorini, but irrigated according to the new ideas. But look how shallow the root system is, doesn't penetrate the soil. These plants are very vulnerable to water stress. These plants can overcome the stress much more efficiently. So it's a big issue how to irrigate. If we irrigate, the important thing is to create a deep rooting that the vine can develop if we work on it. And of course, how to manage the soil, which is also a big issue. If we use grass cover, if we use cultivation, there are opinions for both sides, but it is also a very big issue, and could need a special talk about it. So to close, what's the future? First of all, in Greece, we need meteorological data, and this is very useful. But this program, has provided the area with many meteorological stations, which will provide future data to the growers. Is very important. In Greece, we lack many and representative climatic data from the wine producing areas themselves. Of course, we have to work on our varieties. They have to be more studied in the future, and this is useful not only for Greece, but these varieties will be they will be used in other places as well. This is sure. Sustainable use of all the resources, mostly water. My opinion is that we should not head to irrigation. We have to think about it because we will create plants that will be very sensitive. There are other options like those I showed you, where we increase the resilience of the grapes to water and don't give directly water to the vines. Of course, discover and maybe create new regions in places where today they were considered very cool, that will become in the future very suitable. And of course, keep our growers as informed as possible by seminars and information by the local agronomists. Thank you very much.
Professor Kouras, for your valuable presentation. And of course, this is highly connected, as was mentioned, to our pilot site here in Greece. Thank you all for being here. And of course, we had a structured Q&A session, but we are a little bit out of time. So we will accept one or two questions. If there are any right now, you can send it to the chat or please raise your hand. And then, of course, you are more than welcome to send any additional emails you have to the project's email. You should have received it with your invitation, and we will forward it to the speakers. So I open the floor. If there are any questions that you would like to have for our speakers here today, mainly Professor Kouras that did our keynote speech here at the end. Okay, so we have Professor Giriou, so has raised his hand, so please go ahead, Professor Giriou.
Yeah, thank you, Panagiotou. Professor Kouras, thank you for accepting being here and for your excellent talk. It's very interesting. I don't know if you did follow the overview of our project Germ of Life from the very beginning. We had the chance to discuss about it.
Because I had another obligation in the morning, sorry.
Yeah, well, we had the opportunity to discuss about it also a few months ago in AIO, but as a specialist on viticulture, what would you expect? What would you like to have as an output, as an information from such a tool? Do you consider that it would be something useful to you to facilitate your work and prevent vineyards from drought?
It's a very complex issue. For me, the most important is to create vines which are more resilient. The grapevine is a plant that has a mechanism that can withstand the heat and drought very efficiently. But if we cultivate them like in the old days, the more intensive viticulture in the last years has created vines that are more irrigated, more fertilized. These ones are more susceptible, more sensitive to water conditions, and I think we're spending a very important resource, which is water, which will be very useful in other cultivations or other uses than agriculture, especially with a plant like the vines, which is a plant that definitely has the potential to adapt as long as we cultivate it from the beginning in a less intensive way. When we have irrigation, when we have high drought conditions, we cannot create intensive vineyards because these vineyards are very they demand a lot of resources, and water is one of them. Viticulture must be adapted to the conditions of the area. The grapes, the best grapes always come from the places which are not irrigated. This is a fact.
Thank you very much.
Okay. Thank you very much, Professor Kouvouras, and all the speakers that were here today. So from our side, today's session was really constructive since we had the chance to showcase some of our first results and how we are moving along with the project. And we will have the chance to further discuss our project in the coming webinars. Just to note that our second webinar will take place next week on Tuesday, December 16 at 2 CET. So with this scientific base that was established here today, we are ready now to move forward to the next major topic of the project that mainly is the public procurement aspect. So the next webinar will focus on climate compatible procurement, the co-design process that we implemented during the first phases of the project, and it will also give us the foundation of the vulnerability assessment calculations and tools in order for our last webinar to be able to showcase the in-house tool and how they're created, as was mentioned today, the finalized platforms. So thank you very much. You should all receive the invitation for the next one as well, since you had already registered in the previous one. Thank you for being here, and we will keep in touch. And feel free to share your thoughts or send us an email on our project's emails or through our website with your feedback. Thank you so much. Have a nice rest of the day. Thank you.
Thank you, Panagiotis. Good afternoon, everybody. Thank you for being here with us today. Goodbye.